Record.
Hello, my name is John Cachat, and I'm happy to have a conversation about Quality 4.0. Don't feel overwhelmed, feel motivated. I'm currently the chair of the ASQ Quality Management Division Quality 4.0 Committee, and a lot of what we hear are people getting stressed out, bummed out, frustrated about the technology, and we want to talk about that a little bit. Do an internet search on top industry trends. What you're going to see is a lot of about artificial intelligence in manufacturing and marketing, generative AI, augmented reality, a whole bunch of subjects on it. And that's why we think it's important that we understand the opportunity. One other thing that I'm so happy to see this that I share it in almost every presentation. The Manufacturing Leadership Council's 2030 project report actually had quality as one of the items in their top things that people are talking about. So one, we made the list, which is great. And two, now we're going to try to combine that with this AI 4.0 thing. But there is some bad news. The bad news is a lot of the stuff that we've been relying on for decades are kind of plateaued, kind of stagnated, kind of obsolete. You'll hear people talking about Six Sigma. We'll see, things that we've adopted and latched onto just aren't getting executives' attentions anymore. So one of my points is quality professionals need to engage in the new approaches now. Now, there's good news. The good news is all those things we learned, Lean, Six Sigma, SPC, all those activities we've done have enabled us with analytical tools and expertise, usually stronger and better than other people in the organization. And what we have is an opportunity to share those talents with people to get faster time to insights on all the processes that can get better decision making. And here's just a couple examples. If I showed you this chart, most quality professionals will look at it and say, program B, the one in the red, let's see what they did. They added a bunch of new suppliers. They dropped a bunch of ones that we've used before, and they stuck with some of them. Well, imagine the opportunity to rapidly, and I mean not spending weekends and a whole week trying to figure out what's going on. If the system can come back and say, yes, program B dropped more suppliers, added new suppliers because they were looking at lower purchase price, but the total increase of the actual cost 347%. So what we've known forever and what we've been able to talk about, we now can rapidly deploy and put it together. Let's do another one. And all we're talking about is new product launches, and we want the new product launches to be profitable. Well, here's another one. Show me the impact on the new product launch by engineering changes. So, all right, let's look at this data. The blue guys, program A says, we did a bunch of changes in design, and then some more in prototyping, just a couple in pre-production, and hardly any in production at all. Well, again, we know that a robust APQP PPAP effort with most changes done at design stage is the right thing to do. But to get the actual data and the validation, the metrics that are real versus what I'm just making up here, that would come back and say, oh, by the way, by doing that, the total profit on that new product launch was 227% improved. So we've got the ability, we think this way. Now, is there a way that this Quality 4.0 can enable us to do it better? All right, first thing. The discussion of Quality 4.0 needs to be split into three sections: people, process, and technology. And I think this is very important. That's why I hesitated on how to emphasize this enough. A lot of people are talking about the technology, which is cool, and we're going to talk about a little bit about. But again, the people and the process is the critical component. So let's look at the people section first. All right, here's another frustration, especially with the younger folks that are on the team we talk to. They go, "Oh, John, this, our organization, they don't even want to hear about this." Or actually, I was at another event where somebody said, and then they're not young event, but it goes, our executive team doesn't care. Well, here's why this chart's in here. There are cultures that are early innovators, tech enthusiasts, visionaries that grab this kind of stuff and just run with it. There's other ones that are a little more practical, a little more conservative, and then there's ones all the way at the end that are called skeptics or laggards. Your organization is somewhere in this curve. And by the way, somebody pointed this out. It's not just your organization. It may be different by your department or your executive. But the reason I'm sharing this with you is I don't want you to get bummed out if you're in a conservative skeptic environment and you're a tech enthusiast. If you understand the environment you're in and what you're dealing with, it makes the conversation, I don't want to say easier, but not as frustrating, that you know that there's just different ways people behave. And why people matter, I got two stories I want to share with you quickly. Both of these when I was a co-op student with General Motors at a press metal plant. The first one is we were the first plant in General Motors worldwide to put in a robotic welding line. And at the time, I was a maintenance supervisor, and my maintenance team's installing and doing all this stuff. And boy, there's just like delays and things not working and things getting banged up, and it was a mess. And I finally looked at my team and I said, "Hey, I don't understand why this is taking so long." And they looked at me very open and said, "We don't want it to work." I said, oh, okay, now I get it. So if they don't want it to work, even though robotic welding was the best and the greatest, it ain't going to work. Another one, inspection process. We were one of the first ones to put inline 100% inspection. So a truck floor panel is going down, it checks all the dimensions and does everything. It's supposed to really improve the process. Well, the bummer is it just kept rejecting everything because it was out of spec. And we basically, the operators would turn off the 100% inspection, just keep running parts because we had to run parts. I mean, we have to make parts, right? So again, without talking to the people, understand what's going on, the executive team said, well, we're going to put a red, yellow, green light in the area. And if they turn off that inspection thing, a red light's going to flash and everybody will know it's turned off. The solution to that one was they went over and got a box of nuts, bolts, and dumped the bolts out, put the box over the light, and kept running. So again, we need to understand the people and the process before we just say buying this technology is going to work. Now, the other one is it's going to impact the workforce. I mean, is AI going to take my job? And my answer to that has been pretty consistent. No, AI will not take your job, but somebody using AI might. And that's why we're stressing that the opportunity for us to learn more from it. So this was from the Quality 4.0 ASQ Summit a couple of years ago. I've used it quite consistently, but the idea of learning and adapting, portable skills, adaptable skills, this expertise we have about all of this knowledge. By the way, all of these AI tools have to be taught by somebody. There has to be an expertise that shares with it, that tells it how to ask questions and build relationships. Quality professionals have that and have the ability to really stream with it. The other thing I found interesting, same conference, ASQ conference, is be careful, or not necessarily be careful, but be aware that the human's ability to adapt, to change, is a lot slower than what the technology is. The technology can go through 1,000 different chess moves in seconds. And when I'm playing with my grandkids, that would probably take me months and months to teach them. The idea is exponential technology, linear human. And I'm sharing with that because we need to be aware of the impact on the people. We don't want them to freak out. We don't want them to be overwhelmed. We want them to be excited. And this one comes up all the time. We don't like change. I really disagree with that. People don't like change that makes their life, or they do like change that makes their life easier. Look at the phone, look at any technology. And the classic on this one is, again, people, process, technology. Well, we bought this new ERP app, and it's going to make everything so much better. We bought the technology. We didn't talk to the people. We didn't know the process. And the people that used to do a purchase order in 5 or 10 minutes, now under this great technology, it takes them an hour. Of course they don't like it. It made their job more complicated, worse, not easier. So is there a way that Quality 4.0 will make your life easier? Yes. And it gets more exciting week by week. All right, let's talk about the technology about a little bit. There's a couple different levels. And again, this goes back to your technology adoption curve a little bit. Knowing where you're at, again, just makes it easier. There was a modernization phase, and the people at the end of that curve, the late adopters, are still trying to upgrade old systems. I believe it or not, I saw a green screen AS400 monitor in a facility a couple months ago. They're still out there. But then we're going to try to optimize, make it a little bit better, more efficient, and we don't have to change a lot, just make it better and then transform. And that's what we're talking about now, how the process is fundamentally changing and improving. Now, again, the diagram with the arrow in it is what a lot of people, even the ASQ website, uses these kind of diagrams. And again, my caution is, or I guess my advice is, I think quality professionals need to know enough about the technology to talk about technology experts, but I don't think we have to be quality experts, or I'm sorry, technology experts. And the same thing is vice versa. I wouldn't expect all the technology experts to be quality experts, but we need to be able to have common vocabulary and share the information. You're going to hear things like data lakes and data warehouses and data hubs and data fabrics and connecting all this. I'm sorry?
Beautiful, yeah, I know it now. And આજે પેલા ન્યૂઝમાં તો જો કે ટીવી ના ચેનલ 5 ના તો ડાઉનટાઉન બાજુ તો રિક્ષા દેવામાં એવું થાય કે સ્નો પડવાની શરૂઆત થવાની હોય ને એવું પેલું આમ વ્હાઈટ વ્હાઈટ બધું દેખાતું હતું તો કે ટેકનિકલી ઇઝ ઇન 40s એકચ્યુઅલી આપણે ફરિયાદ થાય એવું નથી આવતું મિડલ ઓફ નવેમ્બર શું ચાલે છે બધું તરબેટ છે.
I'm sorry, if you're asking me a question, I wasn't able to understand what you're getting.
Can you put that in chat, Nicole, and we'll go on. Thank you.
Okay, so anyhow, what we're talking about is some great technology. I was just on another artificial intelligence webinar before this one. I learn more and more every day, but I want to make sure, again, don't feel overwhelmed. I don't expect quality professionals to have to know all this detail. What I do expect is that you can work with the technologists in the space, share with your expertise about, well, I'd like to know that how a new product launches, how engineering changes impacted. I'd like to know how a new product launches change suppliers impacted. That's the expertise that has to be put into tools to make them work. But again, couple words you're going to hear: artificial intelligence. That's just basically making the computer perform tasks that usually require human intelligence. You'll see cameras being connected to them. You'll see that in medical and manufacturing. Anytime you use Alexa or Siri, that's speech recognition. You're going to see some more about decision making. Do you think we should change suppliers? Do you think we should release a change request? Translations, all this wonderful stuff. And again, very powerful tools. You're going to talk about big data analytics. And the biggest thing about this data analytics is a wide variety of sources. Now listen to that again. You don't have to have highly structured ERP, PLM, MES, QMS database structures to start doing some of the questions you want to start asking. The technology enables you to go out to a wide variety of sources and get the data and organize it and let you visualize it and tell some stories about it. One of the things, again, that's really cool is the predictive part. And that's, all the things that we've learned in statistics, analysis of variance, designed experience, all that stuff that I said was, not necessarily obsolete, but by itself, it isn't something people are adapting. But when you take that knowledge and put it into this technology stack, some very exciting things are going to happen. And that's why I think we should be excited. This is a clip I took out of Quality Digest a while back, and basically they asked ChatGPT, will AI make quality engineers obsolete? And what I've been trying to emphasize is it said no, because quality engineers have a deep understanding of the principles, standards, methods, which is beyond the capabilities of AI. And the AI systems simply rely on input for training, validation, decision making. So for knowledge workers, the jobs will change, but they're not going away. All right, let's talk about the process a little bit. Some very simple things you should be aware of, and hopefully you can try after this session today, maybe tomorrow. Take one of the authoring tools. This is out of ChatGPT. And I said, create a procedure for document management for a small manufacturing process. And it ripples through and it creates it, and it's pretty good. Now, is it perfect? Would I just do a file save as and use it as is? No, of course not. But boy, it's so much faster and easier than starting from scratch. One of the other things that's really cool on these document authoring tools is when you get all done with it, ask at the end, did I miss anything? Because it'll go another level beyond it. So document authoring, procedure writing is something that you really should try, like after this call or tomorrow. And then the second part is when I'm done writing it all, it says, oh, by the way, can you create a 5-question quiz used for document management training? And I'll come up and give you the quiz. But remember, in order to make this thing work, a human had to know what to ask ChatGPT to create the content. Quality cost module. This is one of my favorite subjects. You know, quality cost has been around since the 50s, 1950s, for those of you born in this year. And basically, it was just a bunch of theoretical buckets that we said, well, theoretically, you know, if you prevent, you appraise, and you do this, but the only thing we really had data for was poor quality or failures. Now, the only reason we had that data is because we had to tell the accounting system that we scrapped it or reworked it, and we had to tell the inventory system that the impact on the schedule. But remember the big data that I could have access to all this stuff? And imagine the ability to get actual costs at the plant level, at the program level, at the part number level, at the supplier level. Think about prevention and appraisal and failure, all the costs at a level where you're almost like a sports team, a football team, where you can go into the program and say, give me the metrics on how well this is performing. This takes all the theoretical buckets and put actual data in them, and it's very exciting to bring it to life. One of the other areas I've been working on is the production part approval process. This is an area that, you know, was started in automotive, adopted in aerospace, medical, consumer products, et cetera, et cetera. But the majority, and when I say majority, over 80% of the industry, regardless of what you're in, automotive, aerospace, any of them, have binders and spreadsheets that are trying to do knowledge engineering that I've had people tell me in some conversations, John, if they don't give me a better tool to do this, I'm quitting, I'm leaving. And these are highly talented, very smart engineers that get frustrated by this clerical, mundane, routine task. So the idea then says, okay, well, let's go to 2.0. Let's put it in a database. That's a good idea. Take a baby step. 3.0. Let's get single sign-on so it makes it easier. Let's integrate with these tools. Let's do great reporting. And that's cool. But the 4-point thing is really cool because this is where you get to start asking some great questions. I mean, the routine documentation is automated. Humans are now focused on planning and effectiveness review. Here's one for you. Wouldn't it be nice if you could go up to the system and say, can you tell me if any of the PPAPs that we submitted, reviewed, approved were effective? Did any of them actually reduce risk? Did any of them actually work? And again, the reason people are getting frustrated is, you know, there's been stories and told about, you know, 40% reduction in poor quality, 40% reduction in cost. And the majority of the people I talk to said, we're not seeing it. We're seeing negative to 0% return. Now, that's because you're driven by compliance. You're not trying to do it. But Again, this 4.0 technology, when you put it on, it can enable people to do all sorts of stuff that they've never talked about before. Now, there's another technology that I just really want you to think about, and that's referred to as augmented self-service. And here's what we mean by that. For any of you that watch sci-fi, back in the day on Star Trek, you'd have people say, run a level 3 diagnostic. They would talk to the computer, and it would perform a task, and it would come back. So now here's what I want you to think about. Wouldn't it be cool if you could go to the computer and say, hey, we got a quality audit coming up next week, and here's the checklist the auditor's going to use. Can you prep me for it and have it go out and answer the questions and tell you if there's any gaps or weaknesses? We just had a security breach. What should we do? Or, you know, supplier quality engineers are always get frustrated on this thing, but they said, have we dealt with this problem before? Have we seen this? What did they do? What worked? What didn't work? Or as far as documentation, and I'm still shocked. I was in a very, very large aerospace company recently. And long story short, they didn't necessarily have a structured document management system. And until they take this up to 2.0, get it organized, they can't even think about saying, hey, are there any conflicting policies or procedures? Does one say we should do A, the other one says we should do B? Now, can the humans do that? Yeah, of course they can. But wouldn't it be great if the human could ask the question and then the system could give us some information and then we could ask a follow-up question? Here's one of my favorites. I actually did this at a landing gear, aerospace landing gear company I was at right after school, grad school. I was a director of quality engineering. And, you know, you got the, I don't know, 2 or 3 page job description from HR that said, this is what you're going to do. And you say, okay. But I literally went through all the 3-ring binders and brought out everything that says the director of quality engineering is responsible for. And of course, it wasn't even close to what the job description said. These kind of abilities, the things that people have thought about in their career and said, wow, this would be really cool. And then they stop because it's just too overwhelming manual. That's what I want you to get excited about. That's what I want you to see. If any of you have seen The Minority Report, it's a Tom Cruise movie. And it shows them in front of this big screen and waving things around and doing all this great stuff. I mean, access to data anywhere. Well, the whole storyline is about pre-crime, meaning they're trying to solve a crime before it happens. Again, interesting movie you want to look at. But here's what I think when I see it. Well, could quality professionals have pre-problem? So the ability to go through and see all this stuff and anticipate and predict and see, observe what's going on and solve problems before they exist. So again, people, process, and technology, 3 separate subjects, all part of the framework. We need to know what we're doing. Now, I don't want to, I want you to get excited because the future is bright, but we're going to have to learn some new things. And again, I'm not talking about things that are going to make your job or life worse. I'm talking about things that should be exciting and make it easier and let you do things you thought about but you couldn't do before. You are going to have to let go of some of the old truths. You know, you're going to have to stop beating a dead horse on subjects the execs don't care about. And I want you to understand the impact of the Quality 4.0 technology, not the actual technology. Again, I'm not expecting any quality professional to be a quality technology expert. And again, flexible and agile. And you know, I'm in favor of progress. It's the change I don't like. We can make this happen if we talk to the people, understand the process, and apply the technology to make their life better and easier. Takeaways, you know, the old technologies, the paradigms that we've been up to are essentially getting obsolete. Companies that are successfully looking at 4.0 will be competitive, and I think they'll have a workforce that is thoroughly engaged and happy about work, compared to some ones where people are frustrated by doing the same job over and over and over, and it's just frustrating. It's a clerical nightmare. So again, human factors is critical. And on this slide, the only thing I want to emphasize is technology mandates by IT, the IT department, without involving your people and their process will fail, period. I've already had people coming in and or talking to me saying, well, we did this with this and we did this, but it didn't work. Yeah, because you didn't talk to the people, you didn't engage them, you didn't get excited to go. So what you should do, conduct a baseline assessment of where you're at, develop the vision and strategy, build the infrastructure, put some data governance and management around it, or a lot of people call guardrails, make sure you're doing it right, implement the technologies and keep getting better. And most importantly, I guess, it's just either after this call or tomorrow, try an AI tool if you haven't done it. Just pick one. And there's a couple on the slide that can help you. I've got a whole bunch of white papers on all these things. I'm happy to share them with you. And yes, if we have some time for Q&A, I'd like to answer whatever questions we have.
Thank you, John. I'm going to pause the recording.
All right. Hello, everyone. I just wanted to say, first of all, thank you to John for that introductory talk, because I'm excited by the fact that you'll see some of those key topics factor into what I'm about to share with everybody as far as AI risk management goes. So the reason why I'm sharing this topic with you is because I'm one of those rare people who actually started out in technology, and through the technology got interested in quality and quality management. I think I built my first machine learning model in 1997. And then a few years after that, started heading up data science, software engineering, and related topics for a national lab. So I've been doing this for an awfully long time, and I'm really excited that our community is now to the point where we can start benefiting from some of these things and using it to level up and get us to the next place. So there's a few things that we're going to talk about today. I'm going to give you a brief introduction to the whole history of AI so that you have a sense for where the most recent innovations, how they relate to the earlier part of the field's development. We're going to talk about the relationship between AI and quality management. Then I'm going to go into AI risk, and in particular, why it's important now to start managing AI risk, whereas in the past you haven't heard as much about it. So we'll explain why that's the case. Then we're going to shift into talking about some of the things we can do about AI risk. In particular, I'm going to introduce you to the European Union's AI Act of 2024. This was just put in place in August of 2024. And while we're not directly under the auspices of this regulatory guidance, it's important because it gives us a little sense of how the European Union, how the member countries are thinking about AI, how they're trying to anticipate the increased use of AI in their interconnected systems. And so that helps us kind of figure out some paths that the US companies will be taking. In particular, OpenAI, which is the company that builds and manages ChatGPT, they're in the process right now of proposing a similar regulation that'll help maintain the standard of responsible AI as we get into accelerated innovation here. And at the very end, we'll talk a little bit about generative AI, which is the part everyone is most excited about. And I'm going to leave you with a practical tip that'll help you get started with AI risk management, and however you're going to implement it in your local organization. So first and foremost, just wanted to remind you, all of us, every single one of us, already encounters AI daily. In fact, you've been encountering AI daily probably for the past 20 years without realizing it. Every time you open up your email and you have to go into that spam folder to see what the spam is, there is an algorithm that's been usually a Bayesian algorithm that's gone in and tried to figure out, based on the email that you send and the legit email that you receive, tries to figure out what is spam to you. Every time you get a content recommendation, if you're a watcher of Netflix, or if you go onto YouTube, Those are AI-driven recommendation algorithms. Every time you take a picture on your smartphone, there's image enhancement that's AI-driven. And for many, many years, the fraud detection algorithms on our credit card transactions, those are all driven primarily by AI. So the interesting thing about AI is that everyone's really excited about it right now because there's new capabilities, and those capabilities are accessible to a lot of people, which is really the difference. But as AI becomes more widely used, as it becomes something that people expect instead of something that people are excited by, it kind of fades into the background. And that's a very, very important thing that I want you to remember. Because while there's so much focus on the technology, like John said, it's easy to get caught up in thinking that's what we need to know about. But the real focus that will help us advance our companies and advance our own careers, the real focus is on the process. What are we trying to use AI to get done more easily, more quickly, better, or more meaningfully? And that's really the gist of where we want to take it. AI is not new. Matter of fact, the earliest algorithms were created in the 1930s and 1940s, particularly during World War II, but it really got its start in 1956. That was the first time that a couple of leaders in the field, Marvin Minsky was one of them, they decided, hey, we should really get all these people together because I think we're developing a new field. We should start collaborating. So brought a whole bunch of people together at Dartmouth up in New England. And this is where the phrase artificial intelligence was born, because they were trying to figure out, well, what is all of these things that we're studying? They're related to each other, but what is it really? What are all these algorithms about? And that's where AI became AI. In the 1960s, it was really the golden age of algorithm development. Researchers, engineers had access to computing, which they hadn't had before. They were able to try out a lot of the things that they had tested out back in the 40s and 50s. But then, unfortunately, we ended up in what's called now retrospectively as AI winter. Funding dried up. Computer scientists became less interested in AI. And the reason was that there was just so much stuff you couldn't try, right? Everything was theoretical, and the computing power had not caught up to the point where you could really try out those algorithms on practical problems. But then the 90s happened and computing caught up. Of course, we had the internet in the late 90s. By the early 2000s, some of the more advanced machine learning algorithms were already being used to do practical things. And I think the most practical thing is paper checks. So I know that you got to be old to still be using paper checks. I still use them. But you write the paper check and now you give it to whoever you're giving the money to. All of the check processing, all of the image recognition, all of the optical character recognition and the handling of those checks has been done by neural networks, some of the more complicated neural networks, since as early as 2003, whereas it was only 10 to 20% of them before. Now it's all of them. And unfortunately, people just aren't writing as many checks. So that's fading into the history books. In the 2010s, though, the thing that really accelerated progress was cloud computing. Not only did we have the compute to be able to apply lots of these algorithms on the data in front of us, but we could, big data became smaller data. It just wasn't as overwhelming. And then the cost of the cloud computing started going down. So right now, if you're at the end of 2024, we're really in an amazing place in the development that it's easy to get access to the compute. It's easy to get storage space for our data. And it doesn't matter whether the data is stored on your machine or your office's machines or somewhere else on the internet, you can get to it. So we're really at the very beginning. We're just starting this new revolution of capabilities that can help us advance our processes. I want to remind you, though, that even though everyone is excited right now about generative AI, about things like ChatGPT and Midjourney for image generation, there are lots of different categories, lots of different problems that are solved using AI and machine learning. And here are the 8 categories that I like to think about. Computer vision, you see this a lot in industrial assembly lines. Prediction, when we're using there's a fine line between advanced statistical techniques and machine learning when you're trying to use those algorithms to make predictions or to make forecasts. Generative AI is only one of many. And so as we are introducing AI into our organizations, we need to keep our eyes open to make sure that we're not unnecessarily focusing on a tiny area when in fact we could bring benefits to our organizations through any of these areas. So I wanted to spend a couple minutes talking about the link between AI and quality management because this is really, really important to me. I started, like I said, I built my first machine learning model in 1997. And then in 2008, I went to the university and I was a professor of data science and production systems, which was a non-engineering manufacturing degree. One of the classes that I taught from the very, very beginning was applied machine learning. Another one of the classes that I taught from the very beginning was intro to quality management. And the thing that stood out to me was that when we set up processes, when we integrate the people, the process, and the technology, when we continually improve those processes as humans, we're going through exactly the same steps that you go through if you're building an AI to handle some tasks, because the goal is do it better the next time. So continuous improvement in quality management and your models that you train on newly incoming data, they both have the same end goal. So our job is to figure out how to incorporate the people and the technology into our continuous improvement loops. And you'll notice I've back in 2013 I had a article in Quality Progress to encourage people to export their learning at the end of their plan, do, check, act cycles to make sure that everyone around them could benefit from the learning and improvement that they'd gone through. However, there's a little bit more. There's a little bit more. So in addition to quality management and AI and ML sharing the same root of what it is that you want to do with it, there's also another interesting thing. And this is if you think of the history of quality, we started out in the very beginning inspecting the bad quality out. And then through things like Duran's quality by design, there was a shift among practitioners. And instead of just relying on producing these bad things and then throwing them out, let's take a critical look at our process and make sure we're building processes that design good quality in. And then later, the focus on engaging everyone in the organization, the TQM style, became in greater vogue. And back in 2015, ASQ put out a future of quality study. And a couple of articles I wrote responding to that 2015 study, I mentioned, and back then I had no idea how we would do this. But you could see that the frontier we were opening with Quality 4.0 was that we would soon be able to take an approach to quality where we were discovering the best options from a multitude of alternatives. So you can think of this like as doing simulations, right? Or you can think of it as, let's say you have 2 employees and you need to create, I don't know, I'm just gonna make this up. You need to create a marketing message for a particular customer profile. So you have 2 employees and you say, hey, go off and come up with some independent ideas, and then let's bring those ideas to the table so that we can figure out which direction we want to go. Individual people are only going to be able to come up with a finite subset of options. And so, we have brainstorming techniques. We have trees, the trees approach, ways to try and get us to think out of our limited perspectives so that we can generate options. But now with generative AI, we can say, and I actually have a colleague who did this, generate 100 different variations of our ideal customer profile, and then evaluate those against these 10 criteria and recommend which ones meet our criteria the best. So we're now, with generative AI, we're now at the cusp of that frontier where we can think of, instead of let's set the specifications and then let's build processes and products that meet those specifications, we can generate a multitude of options and then evaluate those options against criteria, which opens us up to the possibility of developing things that are even better than we may have specified in advance, which I think is really cool. So really, we're opening up the opportunity instead of just plan, do, check, act, plan, discover, check, act, actually adding a process step where we can explore the multitude of opportunities and find the ones that meet our quality goals. So I think that's a really beautiful time in history to be at, because even though our community has been talking about quality 4.0 for almost 10 years, we're just getting started. You don't have to feel like you're getting behind. Like, we're really at the very, very beginning of it. The number one most important thing to remember, though, is that artificial intelligence, is only part of the context. Anytime you develop intelligence where you're getting better insights or uncovering deeper understanding or deeper meaning, that intelligence is going to be totally useless if it can't get to the people and the systems that need it, and if it doesn't get there in time for them to use it to make critical decisions. So we can never think of AI as a component unto itself. We've got to think of AI embedded in a system that's connected to other people, other systems, and data, and where we use automation in strategic ways to shorten the time it takes to get that critical intelligence where it needs to go. And this is important because it gives us some insights into why we need to think critically about AI risk. Because there are a multitude of degrees of connectedness. In the most basic state, and this could be a people, or excuse me, this could be a person or a system or some sort of data repository. In its most basic state, it's not connected to anything, and it requires manual effort to reach out and to benefit from whatever that intelligence is. But there's a whole spectrum of potentials for connectedness that, at number 10, being deeply embedded in a symbiotic ecosystem where maybe we don't understand what the relationships between all of the subsystems are, but they just work, and they support each other. They bring down each other if possible. It's the most intense degree of connectedness is where you have those ecosystems where multitudes of things are in balance. But there are degrees here. When we connect people to people, or people to systems, or people to data, there are degrees with which we can connect them. Automation also has various degrees. My favorite study that looked at the degrees of automation is actually from 1978, and it is from industrial technology literature. And basically what that says is that when you're trying to create an automation, you don't just have to jump to stage 10, which is fully autonomous operation. The easiest, the most basic place to start with, if you have a non-automated process and you want to automate it, is that you let a computer carry out activities. That's all you do. But then you can get the computer to be a little more integrated into the process, right? They can determine options. They can determine options and ask you if it's okay to carry them out. There's a multitude of degrees of automation. It's not just binary, either automated or not. So connectedness is not just connected or not. There's many degrees of connectedness. And automation, it's not just automated or not. There's many different degrees of automation. Here's why that's important when we're thinking about AI risk. AI risk will increase as connectedness increases because there's more parties that your AI can impact. There's more critical infrastructure that your AI can impact. And AI risk also increases as automation increases. Here's a great example of that. If you've been to one of the cities, I think San Francisco and Phoenix are the only cities that have the Waymo cars. But if you've been to those cities, you can basically get a taxi and hop in, and there's a screen, and you press the buttons, and it takes you where you need to go. There's no driver. The car itself is fully autonomous, and the risk of these vehicles was much lower when the vehicle was in the lab, when it wasn't on the streets, when it wasn't connected by virtue of its proximity to all of the people walking in a downtown of a major city. This is a great example of an innovation that in a limited form, or even in a city that didn't have that many people, the risk increases the more connected that opportunity to take the Waymo drive is to people, and the more automation that's in that car right now. So that's a fantastic example of how AI risk has increased. And to me, this is why we're hearing a lot more about it. This is why entities like the European Union are trying to figure out how to help organizations diagnose and manage AI risk. It's because we are at a stage right now where we're increasingly connected and where there are semi-autonomous systems. So risk is more significant than it was in the past. So you might be wondering, well, why should I think about this? I've been managing risk in my company for a while, but why should I think of AI risk as its own thing? And so we're going to cover some of the reasons for that. So I'm sure some people here are familiar with ISO 31000 that defines risk as the effect of uncertainty on outcomes. But risk is always relative, and that's why I focus so much on the connectedness and the degree of automation, because to assess the risk of something, you have to figure out who or what is going to be impacted by hazards when they become threats. You have to think about how vulnerable are they to what's being introduced. And then you also have to consider the system and the environment itself, because not all systems have the same degree of resilience. They have different vulnerabilities and different capabilities. So the relationship between hazards, threats, and risk is that threats lead to risk, but hazards are inactive threats. So when you're evaluating AI risk, just like when you're evaluating the risk in any other process, you have to take a look at hazards, you have to take a look at threats, and then you determine how severe they are, what's the opportunity for them to occur, and what's the likelihood of knowing whether that threat is being realized. So, same thing with AI as with any other process. I love this example of explaining why risk is relative, thinking about volcanoes, right? This is such a great example of the relationship between hazards and threats and risk. A volcano itself is a hazard. Volcanoes are hazardous, but not all volcanoes are threats. Some volcanoes are, the kind like you have in the Big Island of Hawaii, where when the eruption starts, it tends to go slowly. There's not explosive pyroclastic flows. You can basically tell you have advance warning if that volcano is going to start to impact you. But sometimes those hazardous volcanoes can become a threat. For example, if they erupt often, or if you are standing in a path where there has been a lava flow before, Or, for example, if that volcano has, there's been lots of earthquakes around that volcano over the past, few days, few weeks. The volcano itself is a hazard, but depending upon the conditions that you find yourself in relative to that volcano, that's how threats form. So not only is the threat going to depend on you and your relationship to the volcano, but it's also going to depend on what's the degree of resilience of the community around the volcano, and then what's the perception of risk of the people around the volcano. If you visit places where people live around volcanoes all the time, their perception of risk is, no, this is fine because most of my life it's been fine, and we know what the signals are if there's an eruption. So if ever you're trying to remember the relationships between hazards, threats, and risks, volcanoes are a great way to remember that. There have always been, since the history of AI, dating back to even before the AI winter, there has always been the need to evaluate hazards, threats, and risks around AI, particularly in the 2010s, because that's when people started paying attention to risks that could potentially impact humans. This article is from 2021, but it talks about case studies all the way back to 2011 and 2012, mostly focused around autonomous driving. What happens when those threats are converted into risks because you're connecting the technologies to more communities, or where you're finally having that autonomous taxi available to customers. And I have some stories here of more recently, after ChatGPT was released, its enterprise version was released in March of 2023, making it more accessible to the general public, meaning connectedness increased quite a bit. People started using generative AI to accomplish tasks, but we were able to see some of the risks associated with that. Tony Blair Institute over in the UK was producing some reports, and they know this is a mistake. They used ChatGPT to gather their data. Well, ChatGPT doesn't have data after a certain time period. It's only trained on information that it has up to a point in time. Not only that, but like a language model like ChatGPT was never intended to give you data or to give you statistics. It was never intended to. It's basically a very fancy form of autocorrect where it can predict what the most likely things come next in sentences given a context that you prescribe in your prompt. So Tony Blair Institute learned the hard way, lost some reputation because in these annual reports they use ChatGPT not once but twice to generate statistics which were completely hallucinated, and the readers caught them. There's also a risk of overconfidence. You see this a lot with people on the business side who are now very excited, thinking that ChatGPT and related models will help them build software applications quickly and easily. Well, will it help you build quickly and easily? Yeah. Will it help you deploy those in ways that aren't going to be harmful and that are going to be reliable? Not necessarily. I love this example here that I pulled from the internet because it shows a very, very excited person realizing that they can create a simple app, but when their engineer friend, they tell their engineer friend, hey, anyone can be an engineer now. Engineer says, show me. They provide a link that only can be accessed from their local computer. So, this accentuates one of the things that John was saying earlier, that AI still needs the humans. You still need the expertise because there's going to be lots of aspects of context that you cannot ignore if you're going to deploy AI and machine learning in a way that's beneficial and reliable. Another risk is reliance harm. I don't know if anybody was using Google search when this is probably about 9 months ago. when they were trying out powering Google search with Google Bard, the AI. They quickly turned that off because they realized through people on Reddit making catty comments that they were giving people advice that really wasn't good. For example, you really should not smoke 2 to 3 cigarettes a day during pregnancy, like Google was recommending. It was also recommending in one of its pizza recipes, it said that a key ingredient was glue because it wasn't telling you a pizza recipe for eating. It was giving you a pizza recipe if you wanted to do food photography. So again, highlighting why context is so important. But when you put yourself in a position where you're giving customers or the general public information that could hurt them, that's risk associated with reliance harm. And reliance harm is probably the worst practical risk right now, mainly because people are very unlikely to look to multiple sources for reliable information before they act. Uh, for years, people go to Google, they find a link, they get attached to what the advice is. Now with generative AI, it seems like it should be smarter. It acts a little more authoritative when you engage with it. So the reliance harm is one of the most insidious threats that we face right now with generative AI. Another risk is negligence. This case happened earlier this year in the summer. Basically, Air Canada wanted to be a front runner in its use of generative AI. So within a week of the release of enterprise ChatGPT, Air Canada had a customer service bot and let the customer service bot handle. I think it reduced their number of tickets by 700% or something. They really wanted to get those productivity improvements. So they built a chatbot, put it into production. People started using it. Well, one guy by the name of Moffat, he wanted to get a bereavement fare to go to his grandmother's funeral. So he asked the chatbot what to do. Chatbot said, "Don't worry, just buy a full fare ticket. And then when you get back, you turn it in and you say, 'This was for my grandmother's funeral,' and we'll give you a refund." Well, that was not the policy of Air Canada. Turns out cost this guy a lot of money. He ended up putting a case together going after them, and Air Canada was held liable for misinformation, and they had to, number one, make good with the guy who bought the bereavement fare, and number two, they had to remove their chatbot because this case showed them it is important. You are liable for the accuracy and the content of the information that you provide, which I don't think anybody had thought of up until then. So these examples emphasize as AI risk increases, that AI risk will increase as connectedness and automation increase. Because in the example of Air Canada, there wasn't much risk from the chatbot until they put it in front of their customers. They connected it to their entire market of Air Canada customers, which accentuated the risk. These cases show that there's a lot of reasons that we need to manage AI risk. You're aware of reputation risk. Obviously, there's liability issues, many of which are untested and unproven right now. The increasing interconnectedness of people and systems and critical infrastructure, that's another reason. We're used to having tightly controlled processes, particularly for critical infrastructure. Now, if we introduce AI, especially if it's coupled with automations, we can threaten some of the solidity of the processes that we've had before. When we manage our AI risks, it can help give us competitive advantage, though, because if we are cognizant of what the risks are and we address them up front, that can actually help us release capabilities, release new features and capabilities to our customers, to our stakeholders a lot sooner. Probably the most important reason that we want to think about managing AI risk is just unintended consequences, right? These are new, exciting technologies. People are excited to get them out to customers. We just need to be a little more cautious and slow ourselves down so that we can not only avoid possible negative outcomes, but also capture positive outcomes. The opportunity is the flip side of risk, and I really do think that AI is one of the areas where we'll be able to see the relationship far more clearly. Because just like when we do risk management for a process, we have to decide not just what those risks are, but how we want to handle them. And there's always a number of possible things that we can do, from ignoring the risks, from not even seeking out to be aware of the risks, to the putting effort into mitigating them, reducing them, or eliminating them. So you still, once you outline what those risks are, similar to traditional risk management, you still have to figure out what path you want to take. And sometimes you might start out assessing a risk of implementing AI for your customers, your stakeholders. And I'm trying to think of an example of this that I've encountered recently, but I've actually seen times where, by virtue of collaborating with a team to explore a risk, you actually realize that thing you thought was a risk was an opportunity. And so we have to be cognizant of that. So as we are thinking about how to manage AI risk, I mentioned earlier that we can use the EU AI Act of 2024, which is now in place. We can use that to start thinking about our AIs that we not just build internally, but even if you buy a product and you use it internally, assessing the risk is going to become even more important when we have more regulations in place. So we can anticipate those regulations by looking at the EU Act. The key aspect of the EU AI Act is that they have a risk-based classification system. And so every single AI that's embedded into a process or that's used to supplement human skills is categorized as either unacceptable, high risk, limited risk, or minimal risk. And here's an example of how those are related to each other. At the very, very bottom of the pyramid are those minimal risk systems. And in most cases, it's things like predictive maintenance. Obviously, not all cases of predictive maintenance are going to be no risk or minimal risk because of health and safety risk. But that's many of them that the EU is evaluated right now do fall into the minimal risk category. But as you go up the pyramid, you end up being in situations where the AI can make decisions that strongly impact people's lives. For example, if any of you have either put out job requisitions or have applied to jobs in the past few years, you know that most job applications, most applicants have to go through an AI bot before they ever get reviewed by a real human. And this causes problems both with sourcing candidates and if you're trying to get interviews from the seeking outside. So the encouragement from this EU AI Act is to help us start thinking in terms of where the efforts that we want to invest in, where those fall on the pyramid, because that's going to tell us how much effort should we investigate in really drilling down on the risks that we're introducing when we embed AI functionality into our processes. When I was talking through those risk categories, I mentioned a couple of categories of risks. These are the 5 categories of risks that I use when I'm trying to evaluate risk associated with deploying AI into a process. I look at operational risk, which is how are the people managing the processes that embed the AI. I look at technical risk, which it's only a part of the risk, but unfortunately, people in IT seem to focus all of their time on the technical risk. For example, what's the quality of the data going into building and training the model? But you also have to think about health and safety risk, particularly if those AIs are in industrial processes. Transparency risk is just the risk of not really knowing how it operates, because if you have a problem, if you don't exactly know how your AI is operating or making decisions, you're not going to be able to get to the root cause. There's going to be like an event horizon there. And then I also look at people risk, which is basically two things. First, what is the risk of people using this AI to manipulate processes or manipulate situations? And then the second risk is when people use generative AIs to compete with each other rather than benefit the process or the company, which I've also seen. So those are the 5 risk categories that I usually use. Which brings us to what I want to leave you with today. So I've introduced you to the context and the landscape of AI and some of the risks that we've seen over the past couple of years in the news. But I wanted to talk to you about managing the number 1 risk of generative AI, which also happens to be the number 1 opportunity, which is using generative AI. It is really, really easy to generate stuff. So productivity of content, productivity of, how quickly can you create documentation is going to go way, way, way up. But unless you have the proper controls in place, the quality of your output may go way, way down. So John kind of alluded to that, and I wanted to re-emphasize that now. Here's why. You may have noticed if you're on social media, there's a whole lot of garbage in social media. And you know what? Most of it is caused by uh, people who want to make money off of it, right? Engagement sells. The number of times people watch videos or shorts, that sells because you get paid ad revenue from the companies that you do this with. So there are actual companies in place right now, and all they do is they generate as much AI garbage as they can because they know people are going to be attracted to it and they're going to get paid because of that engagement. The matter of fact, this study in early 2024 found some pages on Facebook with huge follower counts and lots of engagement. They're making money by people looking at indiscriminately produced information. The scariest thing to me, though, is that I think this is going to get worse. I saw an article this summer, you see it on the screen right here, basically encouraging, oh, actually, I got this in email. Somebody sent this to me by email, encouraging me to use generative AI to create ebooks and sell them on Amazon. It's so easy. All you do is press a button and then you can sell it. This kind of behavior is just going to decrease the value of books overall because we're going to have to sift through more and more garbage that people, like grifters, are making money based on in order to get real information. These large language models that are helping us be super productive with documentation and with generating articles, which can be so helpful. The thing we have to focus on the most is that it's really good at generating things that sound great, but none of these generative AI systems are responsible or held liable for the quality of the information, the accuracy of the information they give you. And biggest warning, our legal system, the legal system in the European Union and the one in the US so far is not equipped to be able to make decisions about what happens when someone is harmed from these answers. So we're about to enter a period where there's probably going to be many more legal cases testing out the extent to which you can negligently mislead by getting features and capabilities out the door fast. Here's what I want to leave you with. In order to conduct risk management around your use of AI, you don't have to do much different than what you're doing right now, because your AI functionality will either be used by humans or used by a process. So all you need to do is think about risk management for your process. Like I mentioned in the very, very beginning, the 2 questions that you can ask yourself first that'll help you gauge the additional level of risk your AI is introducing is who and what are the people or the systems or the data repositories is my AI connecting? What is the connectedness? Because the more connectedness, the more risk. Second thing you can ask is, are there any automations going on that are trying to get that intelligence to those people or systems faster? Because those are going to increase the risk. Then take a look at the whole process and just use traditional tools. I use risk priority number all the time. And I also use process FMEA all the time to evaluate the risk of introducing AI as a component of my process. The number one tip I can give you, though, and this has helped lots of people that I work with feel more comfortable about doing risk management where AIs are concerned. The easiest way to do it is to anthropomorphize that AI. Pretend it's just another member of your team that maybe has incomplete information, that maybe doesn't always give you the right information. Think about those AIs as contributing intelligence to your process that's the same as if you asked a member of your team or an expert. And if you think about it that way, you'll find out that it's a lot easier to map out processes that incorporate AI and to do things like a process FMEA, where you're trying to incorporate the additional risk due to having that AI as a component in your system. So I know it was a crash course introduction. Hope I've left you with at least one interesting thing to think about. And I just wanted to say, please feel free to friend me on LinkedIn, because I do have some online courses forthcoming. Also a book from Quality Press next year on AI risk management that I'm excited to get going. So thank you, everybody.
All right. Hi, everyone. So I'm Gavin Jones. I am a principal application engineer with SmartUQ. SmartUQ, we are a machine learning, statistics, and AI company. We're based in Madison, Wisconsin. Our main product is a software package also called SmartUQ. A lot of my job responsibilities involve, consulting for customers using our software, training users on our software, supporting existing users, and things of that nature. So during my presentation today, there's going to be a use of machine learning, and how machine learning can play an important role in getting the most out of engineering data sets, particularly when we're undertaking statistical or probabilistic methods in the analyses we're conducting. If you don't have background in machine learning already, not really much of a problem. The extent of which you need to understand machine learning for this presentation is really to understand that it helps us take input to output data sets. So that could be such as from the results of a series of engineering simulations or engineering tests, and we can train a predictive model with those data sets. And the point there is that the model can then make very quick predictions of what, say, the simulation or the test would produce without the need to run that simulation or perform that test. So the general approach, the general idea that I'm going to be talking about here is, accelerating analyses by first training a machine learning model of the system to be studied, and then using that model in place of the system itself to conduct the analyses more quickly. So for example, we might have a simulation of a manufacturing process, say, or a component we're designing, and that simulation takes a very long time to run. Maybe it takes too long to run to efficiently perform an optimization that we want to do. It's too many iterations to be able to afford that much simulation time. So the idea here is that we then train a predictive model of the simulation instead. We don't run that optimization on the simulation directly. We train a predictive model, a machine learning model of that simulation, and then we use that model in place of the simulation to run the optimization. So again, that sort of approach can apply to all types of black box input to output engineering data sets, experimental data, data collected from manufacturing, in-service parts and components that we have sensor data from, and so forth. The general steps in the process, and I'll later in the presentation go through a simple simulation example that steps through this process. But the overview is essentially, generally we start with a design of experiments to decide which data to collect. So maybe which simulations to run, which experiments to conduct, and so forth. Our objective there is to minimize the amount of data we're collecting. minimize the amount of data we need to collect to train an accurate enough machine learning model. Related to this idea is the idea of data sampling that I'll talk about a little later. So data sampling has more to do with not necessarily which data should we collect, but if we have a lot of existing data, maybe there's a lot of redundancy in that data. For example, when it's collected from sensors, can we identify a smaller representative subset from that much larger data set for the purpose perhaps of training a machine learning model? Then in step two, we train the model and we essentially check its accuracy, quantify its uncertainty. You know, how well does the model we've trained agree with, say, what the simulation or test would otherwise produce? And that's, of course, a very important step in the process because the analyses we go on to conduct with that model are only going to be as good as essentially the predictive accuracy that model allows. When we start doing some of the things in step three, if we're doing an optimization and the model does not represent the system it is meant to represent, the conclusions we come to from the use of that model are not going to be very beneficial. So yeah, in step three, then we actually perform analyses with that model, and there can be a bit of a feedback step from step two to step one if we realize that the model isn't accurate enough for our purposes yet. So we might use different methods to collect additional data to improve the accuracy of the model until it's sufficiently accurate to move forward. So I'll talk a little bit more about the design of experiments piece of this. So the main goal with designs of experiments, at least for this type of workflow, is to minimize the amount of data we're collecting to train the machine learning model. So when we're talking about that use case, traditional methods for designs of experiments like factorial designs, where we're just sampling the corners of the input space, like in the upper left example, have a couple limitations. So for one thing, they're only going to capture linear relationships. So it's sort of poorly suited to training a accurate model for systems that have more complicated response behavior. So systems where there's nonlinearity in the input to output relationship, for instance, which is going to be the case for sort of the vast majority of interesting or complicated engineering problems. Factorial designs also scale poorly with respect to the number of inputs. So a simple problem like the one illustrated there where there's 2 inputs that requires 4 samples. But if we had 3 inputs, then it's 8 samples, 4 inputs, 16, and so on. So the amount of data required scales exponentially with the number of inputs. A more efficient approach is to utilize modern space-filling designs of experiments, which are trying to more uniformly sample across the input space. So an example being in the lower right corner there. And an approach like that can capture nonlinearities. It scales much better with respect to the number of inputs as well. And that approach allows us essentially to probe everywhere within the input space to learn about the response. And I'll say that, oftentimes that that sort of uniform sampling is a good idea as a starting point. But as we collect initial data, as we train an initial model, we might learn that there are areas of that input space that are easy to predict, other areas that are not so easy to predict. And so as we move forward, sampling more targeted to specific regions of the input space can be used for follow-up data collection. That targeted sampling, however, is generally guided and enabled by the information we get from initially probing the entirety of that input space evenly. More specifically, a common type of design of experiments, space-filling design of experiments, is what's called a Lat hypercube or LHD. This is a extremely simple and somewhat unrealistic example on the screen here, but the general idea with an LHD is you first decide how many samples are we going to take, so 3 in this case, and then each of the input axes is divided into a number of intervals equal to the number of samples to be taken. So 3 samples, you can see the horizontal input axis, which isn't labeled there, though, has been divided into 3 intervals. Vertical axis is divided into 3 intervals. And then essentially the sampling is done at random, but there's a constraint that each interval can have one and only one sample within it. So I say this is an unrealistic example because in practice, that sample, for example, to the right there in the middle could be a little down and to the left. The one at the bottom could be a little up and to the right. So long as the constraint isn't being violated, so long as the samples are still within their little squares there. So for that reason, because there, still is the possibility for some clustering, maybe not as much clustering as you'd see with a Monte Carlo approach or a purely random approach, it's very common to optimize Latin hypercube design. So to run an optimization algorithm after the random design has been created, essentially to shift the points around a little bit. Again, try to uniformly sample the space as much as possible while still respecting those constraints. In terms of machine learning models, there's obviously a wide choice of selections you can make in this category. I'll talk about one type of model that happens to be generally pretty useful for engineering data sets, engineering problems. It's called Gaussian process modeling, or sometimes this is called kringing. And it has two benefits. One benefit is that there's no assumptions built in to the formulation of the model in terms of what the expected response behavior of the system being modeled is. So you would contrast that, for example, with, say, a linear regression model. There's nothing wrong with linear regression models. They're perfectly usable in the correct circumstances, but at a minimum, it has to be the case that the system, the data set that you're looking at, has the property that, as you vary the inputs, the output varies linearly or approximately linearly. And if that's not the case, a linear model is not going to be a good choice. It's not going to be able to accurately capture the behavior of that data set or that system. So Gaussian process models, is a non-parametric method like a neural network where none of those assumptions exist. So it'll work well for simple data sets with linear behavior, but probably more importantly, it works well when you're dealing with data sets and response behavior that is, highly nonlinear, doesn't nicely fit into any sort of category. The other thing Gaussian process models do is they make a variance prediction. So it's essentially they predict their own uncertainty in the prediction that they're making. So you can use that to do a lot of different things, add the effects of uncertainty into analyses. Maybe the most straightforward thing you can do with that is it allows you to put confidence intervals around the predictions that you're making. So I'll give a manufacturing example here from one of our customers that tries to illustrate and tie together a lot of the benefits of what I've been discussing to this point. So this is a customer that manufactures jet engine turbine blades. These are very complicated components, very intricate components, very expensive. Reducing scrap is then, very important to them. And before undertaking sort of a machine learning based approach like this, what they would do to decide whether to scrap a part or not was they would scan every blade that they manufactured, and they would essentially compare the geometry of that scan to a database of geometries that they knew had good performance or were expected to perform well. And that's not what they wanted to do. What they wanted to be able to do was accept or reject a blade based on predicting how well that blade was actually going to perform in service. And that information was available to them for any blade that they manufactured, any blade that they scanned. They could get the performance information, but it required them running a series of high fidelity simulations. So things like FEA models and CFD models to assess, mechanical vibration, thermal fluid efficiency, etc. And those simulation models take a long time to run. It's just not a practical approach to do that for every single blade that you're manufacturing. But what they were able to do is train a machine learning model that would predict the results of each of those simulations. And now they can scan the geometry of every blade. They make a prediction with the machine learning model, whether to accept or reject the blade. Basically, they predict the performance of every blade now, and they can do that quickly because it's a machine learning model producing the result, not the full simulation. And this had the desired effects for them. It drastically reduced their scrap, but it allowed them to still maintain their product quality and reliability. So, of course, it dramatically decreased their costs. So I'll take you through a more simple example here where I actually have access to data that I can show you, unlike a real customer example. So this example is a multi-body dynamic simulation of an engine connecting rod. There's 6 variables or inputs to it that basically control the geometry of that rod. And the output of the simulation is maximum von Mises stress during 1 second of engine operation, as well as the mass of the connecting rod. So a model was trained of this simulation, and then I'll go on in the next couple slides to some of the results that were arrived at using that model. So a sensitivity analysis, a global variance-based sensitivity analysis was run on that model. So this sort of analysis essentially tells us how much of the variance in the output do we attribute back to the variation we are allowing in the inputs. And we can set those input variations, however we want. We could set those input variations, for example, to represent uncertainty we have in the value of the inputs, perhaps due to the manufacturing process. And then a sensitivity analysis like this would tell us essentially how much of our uncertainty in the results, so how much of the uncertainty that we get in maximum stress and what we're producing is attributed back to the uncertainty in each of those individual inputs. So the results of this, showed that, a couple of the parameters, the 5th and 6th one, geometry parameters, were most important to driving the stress value. For the mass value, similar parameters, although, the second parameter was also important, and so forth. Another way to look at sensitivity analysis as results is with some of the sorts of plots I'm showing here. So an interactions graph is what we call this. So on these plots, the size of the circles is effectively showing us the same information as the height of the bars was showing on the previous slide. But the additional information we get is that we can see the strength of the two-way interactions reflected in how thick the line connecting any two inputs is. So, for example, the mass output for the second the second input interacts very strongly with both the 5th and 6th input. So we can also do an uncertainty propagation. So uncertainty propagation is a statistical method where we assign uncertainty distributions for each of the inputs. We draw a large sample from them. We make predictions for every sample that's drawn and then look at the distribution of those predictions. So it's very difficult to do something like this on a simulation directly or on a system where it's difficult to collect a lot of data. But if we train a model that system like this simulation, we can do this very quickly and efficiently. So this is just a simple example where we sort of assume there's a nominal design that we're manufacturing for this component. And we've made some assumptions here just for the sake of argument for this example that, the uncertainty in each of those geometries is normally distributed. There's a mean equal to the nominal design. The standard deviation is 1% of that mean. And we want to understand, all right, well, what is the resulting uncertainty in the maximum stress, for instance, as a result of those. And if we look at the results here, we're assuming, okay, maybe again, for this component, we need all the parts to have maximum stress less than 73 MPa. What percent of the time are we meeting that under those uncertainties? And so we can see the histogram of the uncertainty propagation results tells us we're meeting that 99.3% of the time. So again, depending on what we're doing, what are the consequences of, manufacturing a part that doesn't meet that requirement? If it's that something is going to, wear a little more quickly, maybe need to be maintained more often, and it's a very, cheap or inexpensive component that's easy to replace or easy to maintain, maybe we're happy with 99.3%. But if, not achieving that stress means that, there's a high chance of this engine tearing itself apart and, catastrophic failure, we probably are not happy with that, right? So how do we decide where to tighten our tolerances, where to be more efficient in our manufacturing process, say to reduce that, or to tighten that distribution so we're meeting the requirement 100% of the time. That's where we can maybe go back to sensitivity analysis again. So we go back to sensitivity analysis, what are the greatest drivers of output uncertainty? Those are the best targets to have the biggest effect on output uncertainty. So in this example here, I'll talk about the subsampling I mentioned kind of earlier on. So we look at a large data set. We're trying to pull a smaller representative set from that data. So the example data set we're looking at here is for a robot arm that has essentially 21 inputs to this data set. There's 7 joints, each has a value of position, velocity, acceleration. And this robot arm, as you can imagine, there's probably certain functions it repeatedly does, things it does very commonly, other things that, other tasks it performs more infrequently. And if we're trying to sample from this data set of, around 45,000 data points, if we're trying to, accurately capture the behavior of what the robot does, we are going to want to include those more rare cases. And if we simply sample at random from that, statistically, we are very likely to exclude those rare cases. So that's where subsampling techniques come into play, trying to pull a, small sample from a large data set, but that is representative of the entirety of the full data set. So the example on the slide, this slide here is, showing a comparison between, pulling about 1,000 samples at random from this data set versus using a subsampling method to do that. So this is all the essentially 2-dimensional projections of that 21-dimensional input space. And on the right here at the top, we see the same thing, but the random selection. In the bottom right, the subsampled version. And I realize this is all very small, so for the sake of argument, I've just zoomed in on a specific region of the input space. And we see, for example, in that one projection, there's kind of a characteristic heart shape to it. And if we look at the randomly selected data, we can see it doesn't do such a good job of representing, the behavior of the full data set, that, the left lobe of that heart-shaped region is a little more sparse than in the initial data set. If we look at that projection in the upper left, it's a lot more narrow with respect to, the original data set as well. And if we compare that to the subsample data, you can see the subsample data does a much better job of capturing the nature of the original data set. So the last topic I wanted to touch on here is model calibration. So generally, this is getting simulation to agree better with test or experimental data. This could also include situations where you have multiple models, maybe a higher fidelity, very expensive to run model, a lower fidelity model that runs more quickly. You would like to get that lower fidelity model to agree better with the high fidelity model. For the sake of my explanation here, I'll just talk about the first case. They are getting a simulation to agree better with test or experimental data. So there's kind of 2 reasons to talk about why that simulation doesn't agree with the test or experiment in the first place. One of those is parameter uncertainty. So within our simulation, depending on what the simulation is, what it represents, we're going to have different parameters that govern the behavior of that simulation. So things like material property parameters, heat transfer coefficients, stiffness and damping coefficients, turbulence model parameters, and so forth. So there's a question essentially of, what is the best choice to make for those parameters to get the closest agreement with the test or experimental data. And most people that are doing model calibration, most, software tools tend to only focus on parameter uncertainty. So it's either a manual, time-consuming guess and check process of run the simulation, look at the results, use engineering judgment to decide how do we need to tweak things, and then repeat that. Or you can formulate this as an optimization problem, what we call data matching, but other people might have different words for it. But just basically an optimization problem where you define an error metric that assesses the agreement between the simulation case and the test case, and you run an optimization algorithm to find the best choice of parameters that minimize that disagreement. So that process there ignores another reason simulations might not agree with reality, and that is model form error, that there's assumptions and simplifications that go into the constructing of the simulation model. And, if those assumptions are, incorrect, or you've oversimplified things, it might not matter how you pick the values of the parameters. There may be no good choice of parameters that delivers consistent, good agreement with test or experiment. So statistical calibration approaches can address that. They can address the parameter uncertainty and the model form uncertainty in addition to the parameter uncertainty. So I don't want to get into too much detail here, and I realize I'm running a little short on time as well, but essentially you can do this with two machine learning models. So one model you train of the simulation, you use that for basically a data matching approach, just an optimization to eliminate the parameter uncertainty. Once you've done that, you can use that model and your physical data to basically create a training set for a second machine learning model that tries to predict the remaining disagreement between the first model and reality. And that second model, that discrepancy model, when you later go to predict, when you later want to go predict for unknown cases, it can act as a correction factor to the first model. So you predict with the first model, which gives you the most accurate results, having parameter uncertainty limited. You predict with the second model to correct for the additional disagreement due to model form uncertainty. You can also use that second model. You can investigate, you run analyses on it like any other model. So you can use that to investigate maybe the sources of the underlying model form error. Statistical calibration can be done kind of in two main approaches, and I got a couple quick customer examples to illustrate that, but you can do it in a frequentist or a Bayesian approach. So the frequentist approach, the main difference between the two is that the frequentist approach for those parameters gives you a single best value for each one, whereas the Bayesian approach gives you a distribution for each parameter, so it's more of a parameter uncertainty reduction technique. So a couple customer examples talking about manufacturing and the use of calibration. So this is from Boston Scientific, which is one of our customers. It's a simulation of slotted tubes, which are an important component to a lot of other medical device designs. This work, more detail on this work, was presented at the 2019 ASME V&V symposium, which is now the VVUQ symposium, I believe. In any case, just to summarize quickly because of time, they were able to use the statistical calibration to calibrate some of their fatigue models to a set of physical tests, and they used the discrepancy model to help them map and understand the model form error in their simulation. And with that final calibrated model, that allowed them to obtain slot cut pattern parameters that were important to them to use as acceptance criteria in manufacturing. This is a customer example of Bayesian calibration. Essentially, trying to go quickly here because of time. Essentially, they used the Bayesian calibration here, which gave them a distribution for coefficient of friction parameters in their simulation model. And that distribution explained for them essentially the variance and the variation that they saw in their manufacturing process that was basically due to variation in finishing quality and lubrication of the contact surface between the locking mechanisms that they were manufacturing. So it essentially helped them understand that their simulation models weren't bad. It's just simply you need different choices of coefficient of friction parameters to capture what's happening in the manufactured components due to variation. And the last one here, this is a customer that was running simulations for the equipment used to manufacture semiconductors. In the simulations, they had sort of a time-consuming process of getting those to agree with test data. But it would ultimately be accurate, but it was very time consuming. But the remaining problem for them was that the simulations took a long time to run, kind of, too long to run for these models to be used to make on the fly adjustments to equipment and process, which is what they really wanted to do. By the time you ran the model, it was too late to make real-time adjustments. So they trained machine learning models, calibrated those models, so it kind of automated that step of the process a bit more. And the more important thing for them, though, was that because the calibrated models, are just, again, machine learning models, they could make predictions very quickly, which removed that issue with simulation runtime, and it made it possible for them to do real-time process control and optimization. So I'll wrap things up there. I think I went slightly over I cut into my Q&A time. If you're interested in more information on these topics, one resource is our website, smarteq.com. We have white papers, webinars. That's a few examples of things that are available on this slide, but not comprehensive. If you want to try out tools like this, you can request a trial of our software from our website as well. But other than that, I guess with whatever time I have left here, I guess I'm happy to try and answer a couple questions. Thanks for your time.
Hey everyone, so I'm Andrew Ervin. I'm the manager of Generative AI at Eastman, and I'm going to talk today at high level mostly about Generative AI, maybe some of the stuff that we can use it for, and try to hit, at least here at Eastman, some of the big buckets of stuff people are concerned with. I am happy to be interrupted, so if you have questions, you don't need to wait till the end. You just cut me off. It's not going to hurt my feelings any. So with that, I'm going to get in. And again, this is meant to be super high level, so hopefully nothing here scares you. So okay, first, just going to try to hit like what's going on at like a very superficial view. Hallucinations, because everyone seems to be super concerned about them. What are they? What should you do about them, or should you do anything about them? How should you think about them? Security stuff, particularly for those of you who are working in enterprise, there's a lot to think about there. And then I'm going to go and open ChatGPT and do some demos of stuff that I either see people doing or that I think you can do that's interesting with it. So first, it's like what's going on. So in a lot of the context I'm going to be talking about with generative AI here today is language models. Before the meeting started, Arvid was talking some about music generation, and at least big picture, a lot of this will apply to the other ways that generative AI is used. So, okay, so under the hood, there is a technical architecture called transformers that drive most of the generative AI models, not all of them. And okay, so what's going on? So we've got a bunch of stuff here. So you typed in something like artificial intelligence is transforming the and to fine tune them now so that you can just feel like you're talking to a person, but they still work the same way. So, okay, you type in some stuff, you send that off to the model, and what does it do? So it splits up the words that you send to it, and it breaks them up into tokens. So basically just integer representations of the pieces of word or the words. And then once it splits everything up, it builds a matrix representation that basically figures out, hey, which words interacted with each other in a way that's meaningful for the next word. So there's like a pairwise mechanism called attention that says like, hey, this is the important stuff. This is what I should attend to in order to predict what the next word is going to be or what the next token is going to be. So it looks and says, okay, the bottom diagonal of this matrix kind of gives us some hint at what mattered and what would inform the next thing. And then it has some big, complicated, nonlinear function that's fit. And the outcome of that function and the stuff that it paid attention to is it's a list of words or tokens. And so, okay, so it looked at what you typed in. The artificial intelligence is transforming the. Okay, well, I probably need to focus on like the artificial intelligence and transforming more than is and the, but is may matter. And Artificial intelligence paired up together matters a lot. So now what's the next word? Okay, so way, world, lives, whatever. And after it picks a list of the most likely ones, it assigns probabilities, uses a softmax function to sample and say, okay, well, human, that one had 1.43%, and I picked a random number that lines up with that guy. And so then we stick it back on at the text we had. So artificial intelligence is transforming the human. Okay, so that's not a stop token for it, and it just kind of does the same thing again until it generates a stop. So it does this over and over again, and then they spend billions of dollars and train it and tune it, and at some point it starts to feel like you're talking to a person. But ultimately, stochastic parrot, autocomplete on steroids are kind of the terms everyone throws around, and it's not entirely wrong. I think we're starting to move past that being an accurate description of what's going on because they're architecting more complicated models, but it's not a bad heuristic for thinking about what it's doing. Okay, but it's also really good at it, and it's good at it to the point that is not necessarily a useful way of describing it if you're being super reductive. Like you're saying, okay, well, it's just autocomplete on steroids. Well, okay, maybe, but it does some pretty cool stuff, more than me tapping away at my phone, auto-completing my text messages would. So yes, that may be how it works, but that's not what I do with it. And, at some point there's an argument of like, well, what more is there besides predicting the next word or the next token and then engineering systems around it? So while that may be a fairly limited tool set that it has, predict the next thing, that doesn't mean that you can't build a lot of architecture that uses that in the middle that does something pretty crazy. And people are, I think we are. So, but it creates a lot of questions. First off, because it feels like a person, we tend to anthropomorphize it. I certainly do. We tend to assign to it things that it doesn't do. Some of the examples I normally give, I guess they're starting to do, but it doesn't really plan. At least the older ones don't. It doesn't really think. It doesn't have facts and tables that it can go look up, but it feels like it does. And so it's easy to misrepresent what's happening with what I'm feeling when I use it. And as we build complicated systems that use these tools, one of the things that we're regularly seeing and starting to do, so agents are kind of the buzzword of 25, I think that'll be big. And so what you're seeing is, okay, well, the thing that I have it predict next isn't a sentence, it's a choice of a API to call or a tool to use. And then it is spitting out a JSON that has the inputs to that API. Okay. So now what we're doing is not spitting text out, we're spitting a decision out to call the API and how to parameterize it. So now what we're seeing is that people are building into their software decision systems that are driven by big billion-dollar black box language models. And they're selling that as a service, and people will adopt it, we'll adopt it. But there's a lot of agency and security and responsibility concerns that come as a result of that. There's a whole new way of monitoring and testing software that we're going to have to develop that hasn't been a traditional part of our software development practices because we have these stochastic state machines that we're introducing into our code. Then there's just like, how do I use it, and what can it do and what can't it do? And I'll do my best to try to give you tools to think about the answer to that last question, but I don't know that I can even really answer it that well. Okay, so hallucinations. This is a term I really hate, but it's the one that we use, so that's okay. So hallucinations are, fundamentally an alignment question. Is the model, is its response aligned with what I'm expecting? People often are mapping it to, is what it said true, but that's not the effective way to think about what's going on, because truth for a lot of things exists in a gray space that's highly contextual. Things aren't often as true as we think they are. And even when they are as true as we think they are, that's only because we haven't sat and nitpicked the question to death. And then, if you do that enough, you may find a different answer than you started thinking. But there are some things like, what's the integral of e to the negative x, that just has an answer. And it may answer those things wrong. And that's very frustrating for people. And it creates a place where some people feel like, well, I can't use this thing at all because I can't trust it. But I can't trust everything people say, and I trust people more than I trust this. Often people give the wrong answers to things. They say things that aren't true. And hallucinations aren't generally a term I would use to describe the behavior. Being wrong is, maybe lying, but not hallucinating. And so I think it's really important to think about, like, what are we really looking at here? I mean, at its core, a language model, one of the most powerful things it has is being able to be wrong. Brainstorming and helping me dream up ideas, creating code to solve a problem. Those aren't factual things. Those are imagination things. For me, I mean, not for the system, but they aren't a question of true or false. They're not a question of right or wrong or hallucination. They're a question of alignment. Was the answer aligned with my expectation? And so there are definitely places where these are more fragile. Mathematics is one. There's no calculator in the background, at least not unless you cleverly hook it up to a calculator and have it spit out a calculator API call first. There's not a fact table in the background that it looks for questions and answers them. It generates them one word at a time. And so we have tools to address that. And that includes giving it grounding context, and it includes giving it tools to use that can solve some of the places where it's stuck. It's trained on largely like all of the text from the internet. I mean, that's not exactly right, but it's not all that wrong. And then a bunch of research papers and books, but it's a lot of content, and there's a lot of junk, and there's a lot of misinterpretations and weird idiomatic stuff that drives answers that are not aligned with our expectations. And so, okay, so like talking through this, like, what are we really talking about here? We're saying, okay, sometimes I put something in and it gives me a wrong answer, and that's very frustrating for me because I expect a right answer and I don't know what to do with that. And so we have ways to deal with that. But when you use it, and put Copilot here, or ChatGPT, or whatever your works version or application version is called, like, ultimately, right now, this is not a paid employee of a company. It's not a thing with agency. It's a stats model. It's a Monte Carlo simulation of language. And so someone owns a decision, and probably that someone is you if you're using it. And if you don't feel comfortable using it because you think this hallucination stuff is very annoying and off-putting, or you don't feel comfortable using it because it's a domain you don't really know, you probably shouldn't use it. And developing an internal sort of method of, like, how do I vet this stuff is part of the process of going through it. But just, I think, like, a nice analogy here. So I asked the AI for an analogy for hallucinations, and it said, you have like a coloring robot that starts coloring outside the lines, and then it generated this picture. And I think it's a pretty nice example because, like, it's not inherently wrong. It doesn't look good. It's not what I would want it to do, but, like, it's a choice. It might be what someone wants. And so a lot of the time, behavior that's being described as hallucination lives in that space. And then sometimes it's just, like, objectively wrong. But I think that's less true than other people might often think it is. Okay, so how do we mitigate this? So a common way that people have been building around this problem, it's called RAG, Retrieval Augmented Generation. I think it's like a really bad acronym, but again, it wasn't my choice. So, okay, so you can kind of think about, like, what the language models do, like someone taking a closed book test. And so what a closed book test means is, like, we trained all this information into it. It went, read the whole internet, read a bunch of research papers, read a bunch of books, and then now it spits out an answer to your question. But, like, there's a lot of stuff on the internet, and your question could be very vague, especially if you ask questions like I do. Like, my input to these models is usually super brief and not well formed. And so what we're trying to do, what's the common thing, and I'll show some examples of this in a minute, is to move to an open book test model. And so this is to say, like, hey, when you ask a question, the first thing we do is take your question and we break the keywords out of it and we represent that question inside of a high dimensional embedding space. And that embedding space is basically each dimension is some abstract semantic meaning vector dimension. And so okay, we say like 1,500 dimensions of meaning. And we take your question, we put it in that vector space, and then we say, okay, from the content that could answer this, that we have, that could be an internal knowledge base, it could be stuff that we go get on the internet. We say what stuff is very close in that semantic space and what things have a lot of similar keywords. And then we rank them and we say, all right, let's take like the top 10, 15 things, and we'll give the question back to another language model, and we'll give the pieces of answer that we found that we thought were very relevant to the question. We'll give those along with the question to the language model, and we'll let it read that stuff. And then it's kind of like an open book test where you gave it a hint on what page it might find it. And that's not 100% reliable. Sometimes you don't find the stuff that actually answered the question. Sometimes you find it and it still doesn't give an answer that's aligned. But what you do is you reduce the probability of the answer being irrelevant. And so this is super common. Pretty much everyone is doing this. It's like table stakes if you build Gen AI stuff to do this. But it is a powerful way to augment that. Another way that you might do it is you say, hey, look, you have the ability to call a calculator. And when you can call a calculator, you can take your input and write it back out as a series of inputs to the calculator. Then you give it some question like 4 plus pi equals question mark, and then it spits back out, 4 plus maybe 3.14 equals, or maybe it calls to a pi command. And then it calls an API in the background that runs a calculator, and that calculator can take that structured command and give you a number back. And so now we give it the result of the calculator. We say, hey, here's the question you got. Here's the output from the calculator. Go ahead and write the answer. And so by doing that, we reduce the likelihood that, let's say, a 9 is the first digit generated. Okay, so this is like the big picture approach to how do we solve hallucinations. I saw a question pop in chat, so okay, so do AI applications modify algorithms each time it's ran or asked something? Does it store data obtained from questions asked and use that as a reference? Okay, so I'm going to try to reinterpret the question. If I miss it, Wayne, please give me another one. So, okay, so do they modify algorithms each time it's ran or asked something? So the let's say the algorithm, however you want to think about it, that is the model itself. I put text in and text comes out. That does not modify each time it's ran. That is in GPT, it's a generative pre-trained transformer, that the P pre-trained. So they build the model, they train it, they spend billions of dollars training it on cloud compute. The technical resources to do that are crazy. I recommend Meta wrote a very nice paper on their most recent one for reference. At one point, because of parallelized GPUs, they had just like thousands and thousands of GPUs running, training this model, but everything's in parallel. And so you kind of wait for your workers to run, and it gets down to just the one worker. Then it finishes its task and kicks everything back online. And the energy swing from kicking back online was tens of megawatts. So, okay, so they spend tens of megawatts for 50 days training a model, and then they stick that snapshot of a model onto a cloud compute server instance. So that model does not get retrained or modified at the time of inference or immediately after. But then they do gather more data and retrain or fine tune or train a new model over time, those models, and then publish new snapshots. So you have a snapshot that sits in the cloud, it waits for you to ask a question, it runs, it spits out answers, and then every 3 months or so, they pull that thing down and stick another pre-trained model up. Okay, So that's the does it modify algorithms each time? So no. And then does it store data obtained from questions and use that as a reference? Okay, that's a great question. Not inherently. So there's lots of it depends here on this one. So okay, so trying to understand. So there's lots of pieces. So does it store data? Well, it depends on what it is. So the model itself does not store data, at least for most of these models. They are stateless APIs. And so you send something to it, it runs, it sends something back, and it's done. So the model itself doesn't store anything. Now, the people who engineer the thing that serves the model up, like OpenAI, they may choose to store your data and then use that in a future training session or to reuse it as a reference. So, okay, so when does it almost always get reused as a reference? When does it not? So if you're having a chat with it and you ask it a question and it spits out an answer, and then you ask it another question and then it spits out an answer, and then you go to ask another question. Well, because it's stateless, it doesn't have a working memory of what you just asked. But the way that they've got around this is they pass the whole history, or at least a big chunk of the history each time. And so it's not learning off of that. It's just re-getting the information you sent in a packet each time along with the new question, so it can see, here's what we talked about already. Now, they also often, and we build things in a smart way that uses them, let's say, on the fly. So the RAG approach that I talked about that's on screen. So what we'll do is, like, if we're building a system and people are talking and it's going to get very, very long, the conversation. So we'll give them like the snapshot of the thing they just talked about, and then we'll embed the old stuff from the conversation in the embedding space. And every time they ask a question, we'll on the fly go check real quick, was there something before that was relevant, pull that back and stick it in. But again, that's an engineering choice around the model, not a component of the model itself. So hopefully that answers your question. One last thing that I'll tack on, which is the topic of the next slide, is around security. So I mentioned they may store your conversation. So if you go to OpenAI and you can read their data protection policies, the same for Claude or Gemini, and maybe not so much for niche apps that get built in other places, maybe not when you go use something randomly, or when you interact with a model you don't even know is a model. There's a decision that's made by the people who built the system, the website, the place you go, the place the text gets captured. Do they want to store that and build a model with it? So if you go to ChatGPT and you don't opt out of them taking your conversation and training it into the model, that thing that was your interaction becomes future learning. So, or at least it's subject to that. So, okay, so then I have this box here. This is put your world. Often we would refer to this as a tenant in cloud space terminology. So this is like where stuff is safe because you got a hold of it. Okay, so I go to ChatGPT. I leave my world immediately. I send some text to ChatGPT, and that text is OpenAI's to do what they want with, and maybe it's other companies if they choose, or you've elected to opt into it being able to use tools. Let's say Wolfram Alpha or Bing Search, which are two that I have in icons here. So, okay, so Wolfram Alpha has a very nice plugin for ChatGPT, and what that means is that when you turn it on and you start asking questions to ChatGPT, and I say, how much does an elephant weigh? Well, it says, okay, I know that I can use Wolfram Alpha as a tool, and Wolfram Alpha can answer that question. And so I'm going to choose as my output to say, send something to Wolfram Alpha. And then I'm going to write a query to the Wolfram Alpha API that says, how much does an elephant weigh? And then I'm going to send that to them. And so now I've sent my text to OpenAI and to Wolfram. And both of them can take that text and use it to train a language model. The same thing for Bing. Okay, so then if you work at a place that builds stuff, or you build stuff, pretty much all of it happens in the cloud, and Azure for most of us, and AWS or GCP, or Google Cloud for others. So Microsoft, Amazon, and Google are the three big ones. Certainly IBM, SAS, and a few others have their own stuff, but for the most part, Azure is the place we build this stuff. So, okay, so you get an API. And so Microsoft has paid $14 billion plus maybe more now. And what they paid to OpenAI and their investment, what they got for that was the right to compete against OpenAI on OpenAI's intellectual property. So OpenAI spends tens of billions of dollars in Azure compute to Microsoft. Microsoft takes that money, then they build a new model. It's super powerful, and they also have to give that to Microsoft. And then Microsoft hosts that model in their cloud compute infrastructure, and they give you an API. So you send a question to that API, and it runs on a Microsoft computer that's dedicated to you. That's your world, in your tenant. And that's safe. Now, there's some other caveats that I can answer, but like pretty much that's safe. Microsoft may monitor for content for abuse, but you can opt out of that too. So then you can build your own version of ChatGPT or whatever else you want with it. You can have it read your documents. You can do all sorts of cool stuff. And that is safe within the walls of your organization, within your world. It's in your tenant. And so that is not going to be trained by anyone. That's not going to be looked at by Microsoft. It's not going to be used in the model training by Microsoft. OpenAI never gets it. No one gets it but you. And provided your organization has good internal security practices, you can build something that's extremely secure and effective as a tool, which doesn't expose data leakage. So I've given this now Microsoft Copilot. This is true for lots of other applications, but you kind of have to vet them one by one. Okay, so Microsoft Copilot or M365 Copilot. So this is Microsoft is not only selling you the language model as a service that you can use, they also bake it into their products. So it's in Teams, it's in Excel, PowerPoint, Word. It's really good in Teams. It's pretty good in Word. It's really bad in Excel. And then it's kind of everywhere or all over the place for everything else. It also gives you very nice grounding or RAG or search on documents from SharePoint, which can be very useful. If you have bad SharePoint governance, it can also be a huge problem. Now, this also largely lives in the world of your tenant. These language model calls happen on your computer, not on your local computer, but on a cloud computer that you own. And so these architectures are much more secure and much more enterprise ready than just going to ChatGPT or whatever else or whatever other language model of choice you have is. So that's kind of an overview of the security model around this stuff. And so like the short of it is like going out to the internet, bad, paying Microsoft to run it on their compute, good, paying Microsoft for M365 Copilot, good, although there's a couple of other risks that can come with that one. Okay, so I'm going to show some live demos here in a sec, but this is one that we've done a lot with at Eastman, and it's kind of a boring one at first until you start to realize how powerful it really is. So, okay, so all of these language models, and really I think language model maybe isn't even the right word for them anymore because they're becoming image, video, audio, text in and out, and it's much more abstract than language. Okay, so what we can do with these is we can take data that before was extremely difficult to use, to put into models, to make searchable, to get valuable content out of. We can take these documents, this content, and create structure for it. And so this is an example. We've done a similar exercise here at work. And so we fed a bunch of contracts into the AI, and we had dozens of questions that we crafted. And for each of those, we had the language model read the contract and then extract something out of it. Hey, who's the party from our company? Who's the party from the vendor? What's the date that the contract started? And so in this way, what we can do, and you can do the same thing for images, you can do it for audio, you can turn things that were very difficult to generally use for modeling purposes, for just good data management purposes, into something that's very well structured. So, we use this for feature extraction. We take documents and we extract, binary variables a lot of the time, like, did they talk about this? Is this a topic of this document? We create all sorts of structure that then is like very nice and modelable and usable in machine learning applications. So it's super boring, or at least it's not the fun, exciting to show examples, but this is extremely powerful. So certainly you can also translate into all sorts of other cool stuff, but this ability to en masse create highly structured data is extremely useful. And there's some extra stuff that you have to do. So, getting it to reliably respond with just an integer is not as easy as you think. It may just want to say it is 2, or 2 is the answer, or 2.0, or the word 2. And so there's some extra software engineering you may need to do to clean all that up, but that stuff is much easier to solve than taking, a 70-page document and trying to quickly grab 10, 15, 60, 600 structured fields from it. So with that, I'm going to switch over to some demo stuff, but if anyone has a question, please go ahead. And just to make sure, I'm sharing my screen, not the presentation, right? Everyone can see the ChatGPT window.
We see Chat GPT 4.0. Okay,
good. So I'm going to go through a few things here and try to contextualize some of the stuff we've been talking about. So one of the first and most impressive and most powerful things for many of us is using it to help write code and perform analysis. So I'm going to give a quick example. So I'm going to ask it, can you create a synthetic data set and perform linear regression, then create a plot. And so, okay, so this is doing a bit of a few things I talked about. The first one is like, the first thing it does is it says, okay, I'm going to be asked to run code. And so it chooses to call a tool as a first pass thing. And that tool effectively, this may be useful for some, not for others. It spins up a container session. And really what that means is like the code's got to run somewhere, and it's not going to run on your computer. And so it creates a place for that code to run. And then it starts writing the code. Okay, once it writes that code in that container, it's going to run the code. And then if it gets a bug, or it loses connection, it will pick it back up. It looks like my connection dropped, so try again. And we'll see how cursed by live demos I am. So provided my connection stays strong, it will write the code, run the code, and then hopefully give us a nice plot back. And of course, okay. I'm going to try a new conversation one more time. And so one of the things that is useful here is, as it's doing this in the background, it does show the code it's writing. So you can come vet it, see, how did it synthesize the data? How did it prep all this stuff? What did it do? Okay, I like the code, and it's analyzing, hopefully not going to crash, and it'll spit out an answer here in a second. Okay, well, this is unfortunate. Fortunately, though, I've prepped for this and have examples. So I'm going to go pull one down. Oh, there we go. Okay, problem solved. So it runs the code, generates a plot, returns the plot. I can take a look at it. I could say, maybe I want and get me. So I can tell it, hey, I want to try Bayesian regression. I want you to also use my preferred library of choice for how you do it. And that's a bit cooked because I know it has that one in the background and not the one it'll try to use. And then it'll update the plot. And so we get OK plot that runs. And so, OK, so what can we do with this? Well, first, you can iterate very quickly. You can upload files, so I can send it an Excel file. And of course, again, if you're working with company data, I don't recommend doing this without building something or buying something that's a bit more secure. But I can give it some data and say, hey, I want to perform some analysis on this. Now, I wouldn't trust it to do something I don't understand. I wouldn't trust it to make a decision for me. But if I want to really quickly visualize some data and maybe I don't even know where to start, maybe I know where to start, but I want to look at a lot of different stuff and I kind of want to rush through it. Maybe what I really want to think about is, hey, I want to try like 5 or 10 or 15 different things, and I want you to create a bunch of plots for me along the way. This is very nice for that. And honestly, I'll see if I can get a good example of this next thing. So I'm going to try, let's do some network optimization. Give me start of a problem in text. Okay, and so it describes a network optimization problem here for me. And, this is a lot faster than if I tried to type this up myself. And so sometimes if I give it a problem like this, actually, this was probably too good for what I was getting ready to say. The next step it'll do, if I ask it, hey, can you run this, is it'll come back and say, oh, well, I don't really have everything I need. And it can help you think through problems. Now, it's still not going to think through, it's not going to think at all. It's not going to list every potential shortfall of your approach. It's not going to call out, hey, your assumptions are bad or your data is bad, at least not with any reliable guarantee. But again, if you want to really quickly spin up an optimization problem because maybe you not worked with linear programming that much, and so you say, okay, can you write out the code for me? And so you can imagine I had typed out this whole problem, and now I can have it start writing out code for something I kind of understand, and I can very quickly get to troubleshooting or thinking about adding some complexity. And at least for programming, it can solve some very tough problems. So while it's working on that one, I'll show. So this is a problem. It's one of the tougher problems on LeetCode. There are harder versions of the problem, and it's a super simple one to think about. There's a nice picture here. So it's the in queens problem. So if I have a 4x4 board and I stick 4 queens on it, how do I put them so that they won't attack each other in one move? So this is a tricky NP hard problem. You can make it harder by saying, let's make it a prime by prime board where no 2 queens are collinear, and that makes it much tougher to solve. It makes it unsolvable for some n. But look, this is a really tough problem. Hey, write it in C++ for me. And then I might come back and say, hey, stick in a bunch of heuristics and show me how to do this. Okay, so that is a way to really get some value out of this if you are a data scientist or an analyst, because it can quickly get you to, here is a path at solving a problem. Even if you maybe don't fully understand something. So, probably everyone here has heard the law of large numbers, central limit theorem. Maybe less have heard the law of the iterated logarithm. So help me understand the law of the iterated logarithm and where it sits relative to ln and central limit theorem. And so it can give us a very nice breakdown and the proof, and even if you haven't had measure theory, it can give you a much more explainable answer. I may have overdone this with O1 preview, but this is a nice example of what's coming next. So I talked about how these things are kind of like autocomplete on steroids. And we may or may not be seeing a scaling law limit where autocomplete on steroids starts to break down and you throw more compute and more data at it and the model doesn't get better. And so a way they've been working around this is to spend more money on inference compute. And the way that works is in the background, they've hidden the fun stuff away from us. There are several intermediate calls in a specially tuned model. And those are to think step by step through how you would solve the problem or how you would answer the question. And so it's to plan and to lay out an approach. And so for each of these bullets, clarifying the concepts and breaking down law of iterated logarithm, etc. So in the background, it's actually doing a bunch more text generation about each of these things until it feels like it has sufficient information to answer the question. And then it takes all of the context that it generated and a bit it eats its own lunch and goes and takes that and then feeds it to another model which generates something. But the end result of having it do this, what's called chain of thought or this sort of planning step, is a huge step change in model performance, especially for math, programming, and science-related tasks. It got a lot better. And so, okay, so now we get some very nice explanation of the law of large numbers, of the central limit theorem, of the law of the iterated logarithm, and then maybe I say, I don't know what almost sure convergence is. Help me like I'm an engineer. I have an engineering degree, so no offense to the engineers. So, and then it can help break down the concept. So, this is a lot of the practical application. It's for, at least for those of us doing data heavy things. It's integrated into our IDEs. For those of you who aren't huge programmers, it's very helpful for thinking through tasks and supporting, but it certainly is no substitute for smart, qualified people, at least not yet. It can also create pictures and songs and interpret pictures. You can take a screenshot of one that I've used that's actually been super effective. You can take a screenshot of a diagram, have it explain the diagram, have it create something from that. I had a PowerPoint presentation here at work that someone had made that looked very nice, and I was building a web app, and I gave it a picture of the presentation and said, hey, write this in HTML for me so that I can have some version of this on the landing page of the app. It did. It looked terrible. I took a screenshot of the app and said, hey, here's what it looks like. You really messed it up. Please fix this. And 2 or 3 rounds of that, it had produced something that looked better than the presentation, but very close. And so there's lots we can do. But I think probably for this audience, the biggest application is using as analytics assistant. Some advice I've given to people often who don't know how much, I don't know if trust is the right word. They don't know how to think about integrating it into a workflow where they don't want to hand off too much. They don't want to hand off too little. I think a good way to think about it is like a super smart intern that maybe doesn't get the bigger picture. I don't care how smart an intern is. I'm not going to take something from them and throw it in front of a vice president without vetting it. But, that's not to say I wouldn't give them something pretty arduous and let them, take a shot. I think that's like not a bad way to start using this. So happy to take any questions if you got them.